the branch space. If you have seen this before, this should be fairly natural, but if you have not, this should be fairly non-natural, so I expect you to learn this in 1 minute. It's a lot of time to learn, but bottom line is that you start with a base function that you call E, right? This is an entire function, and throughout the next 2 slides, I'll always write E star as E of Z bar bar. A Fermi Taylor function is an entire function that satisfies this property. E star Z is less than E of Z in absolute value for all Z's on the upper half plane. So E of Z is bigger than E of the conjugated Z, all Z in the upper half plane. So this is the Fermi Taylor condition. A typical example is when you consider this E of Z equals E to the minus I pi Z. Actually, this function here will give you the Philly unit space, right? And the Brunner space is actually the space which I'm calling H of E, is the space of entire functions F, such that this L2 norm on the real line is finite against this measure E of x minus 2dx, and such that F over E and F star over E have bounded type and non-positive type on the upper half plane. Bounded type means that they can be written as the quotient of 2 bound and analytic functions on the upper half plane, and non-positive mean type, for any function of bounded type, you have a so-called Levin-Lina factorization, and this mean type pops up with this quantity here. You might have seen this with a different constraint. You can also say that this function F over E and F star over E belong to the Hardy space H2 on the upper half plane. This is probably equivalent to this. This is a Hilbert space. When E of Z is equal to this function, this gives me exactly the Philly unit space. As a matter of fact, when the space function that you start E has exponential type, so this is essentially the space of functions that have exponential type less than or equal than that function, such that this norm is bounded. More than that, this is a reproducing kernel Hilbert space. The evaluation function of R continuous, and this is the inner product, and if the reproducing kernel is given by this expression here. Right. If you label A to be a half of E plus E star and B to be either to E minus E star, then you can write E of Z as A minus ID. A and B here are real entire functions. They are functions that are real on the real line. So you just write E as A minus ID. The reproducing kernel has this expression here. Right. And if you evaluate F at the point W, this is the same thing as taking the inner product of F against the kernel K of W dot. I'm using the parentheses here. The inner product of E, right? Let's see what happens when I take E of Z to my E to the minus pi I Z. Then my Lagrange space is just the Philly unit space. This function A here is just cosine pi Z. This function B is just sine pi Z. And this reproducing kernel K is the one that I had before, sine of pi Z over pi Z. Right? So everything makes sense. What is nice about these things is that, before I move to the next slide, remember I showed you the second proof where you have an L2 method using orthogonality to exploit the problem. Here, you have an orthogonality also, right? So the orthogonality relation that one has to use here is that these functions here, this function that I'm calling K, well, the chalk is solving, so I don't think I can write here. Yeah. We have this chalk here. So this is this function's K at the point C dot. They are orthogonal as long as you take this C to be the roots of, say, A, or the roots of this function C. They're orthogonal in this space. So this is the relation, the orthogonality relation that you need to use. You use that. This function else here, this nonlinear function else here. I'll have my hand over to the... Alright, so what can we do with this? So I told you that we can solve it for weighted measures, but we cannot do for all sorts of weighted measures. We can do just for measures. We can solve the original extremal problem with measures du being given by this, e to the x minus u dx, where this function e of x, which is the Hermite-Euler function, satisfies some technical properties here. So we have to have bounded type itself, no real zeros, the function e of I is to be real entire, and these companion functions a and b that I defined in the previous slide cannot belong to the space, so that I can use the orthogonality property. So this is well known in the theory of the branch spaces. Now, and just to state you what we did over the last 2 years, so this is my work with Friedrich Schlickmann, we solved this problem for the exponential and the Gaussian, and we can also integrate the parameter lambda. And with my student Felipe Gonçalves, we solved this problem now for the odd implicated exponential and integrated the parameter lambda. And with Fashion G, Friedrich Schlickmann, Michael Milinovic, we solved for characteristic functions of integral. So this is, the classes of interest, at least for me, even functions found truncated and characteristic functions of integral. I'll show you a little bit how to apply these things. Well, you might say, well, these measures are not exactly generic measures, right? I mean, like, can I give you a measure and you can say that you can write like this? Not exactly. But this is where, and why I find this so beautiful, where the whole magic happens. So, let me give you a very bad example, nasty, you know? You might start looking at this function, and you guys are working on Bessel functions like this. So this is, you consider this function a nu and b nu just to be Bessel functions, multiplied by certain quantities. So this is the functions related to the Bessel functions j nu and j nu plus 1. Right? And you form this function e nu by saying a minus id. So these are real entire functions, you take a minus id. I claim to you that this is a Hermite-Euler function that satisfies my technical properties you want to form the previous slide, and this is a function of exponential time. This is actually exercise 228 of the branches book. I'll tell you the story about the branches book later. But whenever you take a function over space, you're integrating as two guys, you need to measure with the same number. So that's what allows you to solve, for example, the original extremal problem with this measure, because ultimately you will do a 1 or 2 reduction of the Lagrange and bring your functions to this Lagrange space. And here you have this measure right here. Alright? So this is what we do. So what we can solve in the multi-dimensional case, we can solve it for the exponential and the Gaussian, and a class of radial functions. Now I'm using the bold font to mean several variables. And we can integrate with the parameter lambda. We can consider now any sort of power measure, x to the power dx, or any sort of measure of that type, because, well, when like compact convex set is the equivalent ball. But here you have to do a symmetrization. If you want to measure as a function in several variables, what you do is that you can symmetrize your measurement using the group of rotations, and you make your measurement radial, and then you bring the problem to a one-dimensional problem with a different measure. You gotta pay this price here, multiplied by x minus n plus 1. So as long as you fall with the original problem on the real line that you knew how to solve, you are okay. Alright, and then my two students, Felipe Gonçalves, Gustavo Padilla, and Mike Kelly from the University of Texas, are doing this anomalous problem, but now not with KD in the ball, but with KD in the cube or parallelepiped. Right? Just to show you a little bit how this thing is, well, I think we got a pretty good knowledge about this problem, what's going on. There's a lot of nice questions open here that I don't know the answer yet, and one is very simple. It's called what's the problem? So let me give you a generic compact, convex, and symmetric set on our end. And I ask you to solve the one-level problem with respect to that compact convex set, meaning what is the best non-negative function such that f of 0 is 1, which has the Fourier transform support on that k. Minimize L1 all of that. Say if k is an epsilon on R2. I have no idea what the answer is. Right? I believe that the answer should be inversely proportional to the volume of k. And my only belief for this is just that I know how to solve for volume cubes. And it seems to be the case for this too, but I don't know if this is the answer in general. You can give it some thought. Okay, so this is an mathematical constructive function theory. Now let me show you a little bit of how we apply these functions. Right? So I'm going to give you two applications. The first one is to use these functions to give some bounds for objects related to the Riemann zeta function under the assumption of the Riemann hypothesis. Right? So the basic objects that one wants to consider here are the basic objects of a complex valued function are the absolute value of the function and the argument of the function. So this is what we're going to do. So assuming the Riemann hypothesis, in 1924 proved three interesting bounds, and the bounds are in red here. We first found the bound for the modulus of the Riemann zeta function on the critical line, z of 1/2 plus it, s with very log of this is less than or equal to log t over log of t. S of t is the argument of the Riemann zeta function at the point 1/2 plus it, well, it's actually 1 over pi times this argument. I also proved that this is less than or equal to log t over log t. So this argument, the way you do this argument is that you start at the point 2, that you know that z of 2 is a real number, you baptize the argument that to be 0, and then you go from 2 plus it, and then to 1/2 plus it, and take the continuous variation of this argument. So this is what I'm calling S of t. And you can take another quantity of interest here is the antiderivative of the argument function, this function I'm calling S1 of t. So we would also prove that S1 of t is less than or equal to log t over log t squared. So these are the three Littlewood estimates in red. These estimates were never improved in 90 years, never improved in the order of magnitude. The order of magnitude is still this. The only improvements have been on the constant that one can place here in front. And I'm stating here that what were the best constants up to a recent date. So for this first estimate, the best constant was due to Sander-Arajan in 2009, 1372. For this one, the best constant was of course from Goldstone and Gonen, 3.5. And for this one, the best constants were due to Fuji. Well, these are two constants. On the positive side, 0.32, and on the negative side, minus 0.51. We have improved these three results, and here it is. So the first theorem is due to Flesch-G and Sander-Arajan, 2009, and improved the constants for the absolute value of z of 1/2 plus it. They replaced the 0.372 by log 2 over 2. And then for the argument for the S of t and S1 of t, we improved the 1/2 to 1/4, and we improved the other constants by placing this optimal 5/48 and 5/24 optimal with the existing methods. So this is an improvement of 1/2 on the previous constant, and this is roughly an improvement of 8 times what were the previous constants. Now, the idea to prove these three results is essentially the same. It's to reduce the problem in number theory to a problem in Fourier analysis. And the idea is to, you have a representation lemma, to write your object, the object that we're considering, as a known function of t. So you want to evaluate this object at the height t. You want to write it as a known function of t, minus a sum over the zeros. So these gammas here are the imaginary parts of the zeros of the zeta function. So I'm assuming the Riemann hypothesis, so my zeros are 1/2 plus I gamma. So I can write my object as a known function, minus a sum over the zeros, plus an error term, 0 of 1. And these functions that appear here as the sum over zeros, functions that appear in this first one f, then here g, and then here h, these are not random functions. These functions have a certain nature connected to the problem. So the function that appears here, f, is equal to log of 1 plus x squared over x squared. This way the function appears here.